Dr. Segan here, along with Luna. She insisted on being in my lap as I film this. So today, uh, we're going to start talking more about the meat and potatoes of environmental science. So actually about Earth and the environment. And this is kind of a hard subject to start, to be honest, because Earth's really big and it's all interconnected and lots of things, plants, animals, rocks, water, air, all this stuff kind of going on at the same time. And so it's kind of like, where do you even start? And so where I like to start, and I kind of think it gives a unique perspective on things, is with some space science and about the formation of Earth and how Earth has changed over time. And you kind of get a feel for the rocks and the water and the air and the animals and the plants as you sort of go through that process. So for this lecture, we'll focus on Earth in terms of space science. So basically, where did Earth come from? And what is Earth's place in the universe? And so that's what we're going to call it. We're going to call it Earth Perspectives on Space and Time. So let's jump right in. All right. So, to understand Earth and space and all these things, we really do need to kind of work on our ability to process big numbers. And that's where we'll start today. We may use, words that I think, up to 1,000 or maybe 1,000,000 we can kind of process. But once we start going to billions and trillions, I think a lot of people don't really realize the difference between those things. For example, over here on our right, you see 1,000 squares. One big square made of 1,000 smaller pictures. So you could count those all. That's 1,000 tiny pictures. I think the human mind can kind of grasp 1,000 pretty easily. When we start talking about 1,000,000, that's 1,000 times 1,000. So if we took 1,000 of these cubes on your right side of the screen, if we took 1,000 of those, then we would have 1,000,000 smaller pictures. If we had to take 1,000 of these cubes on a typical laptop screen, I'm measuring my cube at about 12 centimeters. So if we took 1,000 of these cubes and made 1,000 of these squares and kind of made one big square out of it, it would take, this is a meter, so to take 1,000 of those squares on your screen, we would need about 4 of these by 4 of these high, or about 13 feet in each direction to kind of see 1,000,000 of the tiny ones, of those little tiny cubes. So you can kind of see that, well, that's a lot of cubes. It's kind of hard to imagine 1,000,000 cubes. You would need that tiny little cube on your screen down there. Each one of those little tiny pictures, you would need about 13 feet by 13 feet of them at that size to get to 1,000,000. So 1,000,000 is a hard number to wrap your head around. Some people have $1,000,000. I can't really imagine what it would be like to have $1,000,000. That's wow. That's a lot of money. And a million of these little tiny cubes is really hard to imagine. Okay, when you get to 1,000,000,000, now that's 1,000,000 times 1,000. Okay. All right, now all of a sudden, instead of needing keeping these cubes the same size as they are on your laptop screen, on a typical laptop screen, now all of a sudden you need over a football field length of cubes spanning in each direction. So you would go with a football in each direction. So if you somehow could superimpose this over, say, like a big football field and kept all these cubes the same size as what you're seeing right now, that would be 1,000,000,000 cubes. So basically, the size those little cubes are on your screen, if you were to keep them that size and then fill up about 2 football fields with those, of that size, little tiny pictures, if you put that over the entirety of the football field, you filled the entire thing up with those little tiny squares, those little tiny pictures, uh, then that would be 1 billion cubes. Wow, okay, so that's a huge number. And then a trillion is even more unimaginable. 1 trillion cubes, you're talking about, I don't know, filling up the entire, city of Houston with these tiny little squares on your screen. And that would be something more like 1 trillion. So as we refer to these things, there is a huge difference between 1,000, which you're seeing on your screen, 1 million, which you would need 13 by 13 feet or 4 by 4 meters, 1 billion, which you would need to fill two football fields with, and 1 trillion, which would like fill up the city of Houston. So there's a huge difference between these numbers, even though there's only like one difference in the letter. Anyway, with that in mind, let's talk about our universe. And I'll tell you a little bit more what I mean by universe, but basically not only our Earth, but also all of space around Earth is the universe. And using kind of these big numbers, the first thing we're going to learn about space is that our universe is really big and really empty. So I'll give you some perspective on that. The Earth is pretty big. I think we're all familiar with the unit of a mile in this class. Earth's circumference, which means all the way around one time, is about 25,000 miles. So if we started in Houston and we started going, west towards California, and then we went all the way across the Pacific Ocean, all into Asia and over into Europe, and then we crossed the Atlantic Ocean, then we came back to Houston, that would be 25,000 miles going all the way around the Earth. The sun is considerably bigger than the Earth. Its circumference going all the way around the sun is about 3 million miles. So you notice that we've changed from 1,000 to millions. So that is a lot bigger. But when you go from the distance from the Earth to the sun, now you're all of a sudden talking about 93 million miles. So it's just a huge, huge gap. And the distance from Earth to Pluto, which is kind of the most outer planetoid thing in our solar system, it's 3.1 billion miles. So now we're moving up to a B. And then if you're talking about, okay, going outside of our solar system and away from all the planets in our solar system to the next star out there, which is called Alpha Centauri, that's 25 trillion with a T, R, billion miles. So there's a huge difference here, and most of everything in between these huge distances is just emptiness. There's just really nothing there. And to give you a little easier way to wrap your brain around how big an empty space is, let's talk kind of a simpler term. We know that, we went to the moon and we go into space in these space shuttles. And the typical space shuttle speed out in space is about 25,000 miles per hour. So at 25,000 miles per hour, that means it's going 25,000 miles every hour. It could go around the Earth in about 1 hour. Now, when it's in orbit, that's the distance a little bit further, so maybe it'll take it 2 hours or something at that speed if it's in a high orbit, or 3 hours, depending on how far up it is to go around Earth. But, these things move fast. Typical airplane moves at about 500 to 600 miles per hour. So 25,000 miles per hour, it's way faster than an airplane. And so, it can go around the Earth really quickly. And if it wanted to, let's say if it got to the sun somehow and it was going around the sun is considerably bigger than the Earth. At that speed, it would take 5 days to go around the sun. So you can kind of see the proportion of the sun to the Earth. The sun is way, way, way bigger than the Earth. It would take 5 days to go all the way around it, even if you're going super fast. If you wanted to travel to the sun, even at this blistering fast speed of 25,000 miles per hour, it would still take 5 months to get to the sun. And even more mind-blowing, to get out to Pluto, it would take you 14 years. Yeah, let me say that again. It would take, at the normal speed that we would travel to like the moon and back, or to a space station and back out there in space, it would take 14 freaking years to get to Pluto. We've actually sent spacecraft out to Pluto, and yeah, I think it took 9 or 10 years to get there. It was going a little faster, but yeah, Pluto is really, really far away. And then to get to the next star, if we wanted to go beyond our solar system and we wanted to go past Pluto and we wanted to find the closest thing out there, that would take over 100,000 years. Unbelievably big space in the universe. And for that 100,000 years, there would virtually be nothing in between us and that star. I mean, there's a lot of little dust particles and stuff, but in terms of like planets and, well, there are no stars or anything like that, there would just be nothing. So it would be 100,000 years of just emptiness trying to get to Alpha Centauri. Doesn't sound like we're going there anytime soon. So, you know, the sort of map of the solar system that you see up on the wall in elementary school class, well, that is horribly inaccurate. You could not really visualize the solar system in any kind of poster if you really wanted to keep it true to its actual nature. A better depiction would be something like this. So if that big orange ball is the sun, these would be the size of the planets. And I think this little blob right here in the center, the third one out, that would be how big Earth is compared to the sun. So you can see the sun is huge, and compared to all the planets, it just completely dwarfs them. And even some of the bigger planets like Jupiter and Saturn really dwarf Earth. So we are really a pretty small little speck floating out there in our little solar system. And if we wanted to put, so this would be a better poster to put up in people's classrooms if we wanted to get a better idea of how big things were out there. However, you can see here at the bottom, it says interplanetary distances are obviously not to scale. And usually I do this in a classroom where I project this image on a board and the sun is, you know, like 3 feet wide or something on the board, on the projector. And if you make the sun like a 3 foot wide ball in on Westbury High School's campus, Pluto would be almost on the other side of Houston. I mean, so the idea that you could have any sort of illustration that actually captures the distances involved and the sizes involved of the solar system, we really truly can't really imagine what it would really look like, because it's kind of absurdly huge and empty is really the nature of the solar system. And then there is what's beyond the solar system. So if you go camping and you're way far away from the city lights of Houston, and you're way far away from all the pollution of Houston, and it happens to be a clear night with no clouds, and especially if maybe you're like high up in the mountains or something, it's really dry air out, you can see unbelievable numbers of stars out there. And it's kind of crazy to think about. Right now above your head all this stuff is, but we just can't see it because of all the both light pollution and air pollution in Houston. So what is all this stuff? How big is the universe? So I have a video that's made by a physicist who was trying to help people visualize and understand how big the solar system is, and also how big the stuff outside of the solar system is. And I'm just going to play it for you, and I think you're going to like it. So, you know, we start this video on kind of conventional scales that we're used to. We're looking at a person and we're kind of zooming out on a park that's in a city of San Francisco. And, you know, we're still on scales of like kilometers, which are a couple miles each. So, you know, and then we're zooming out more on California. And I think we've all used Google Maps. We're kind of familiar with the map of the Earth. And now, you know, now we're kind of zooming out on the size of Earth, and we're talking about the scale of tens of thousands of kilometers, and we can zoom out even more, and eventually we'll find our moon. And you'll notice you know, the moon is pretty far out there compared to the size of Earth. I mean, the moon's orbit is massive compared to Earth. Um, but that's where the moon would be. So we're going to keep zooming out, and it takes quite some time before we get to sort of some nearby planets. I mean, at this point, you can't even see the moon orbiting Earth, and Earth itself would just be a tiny little speck on your screen. This is actually not to scale. Um, and you can see just how far away something like trying to get to Venus or Mars would be compared to getting to the moon. It's way, 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 way further. And now we kind of can zoom out to the entirety of our solar system and some nearby spacecraft that we sent out there. This is Voyager 1 and New Horizons. These are our deep space exploration crafts. I don't know much about New Horizons, but Voyager 1 was launched in the late 70s, and so it's been cruising at about 35,000 miles per hour for, you know, over 40 years, and that's about where it is compared to the rest of the solar system. So it went by Pluto, I think, in the 80s at some point, in the late 80s, and then it's just kind of out there beyond Pluto, and you know, there's really nothing out there. It's just kind of cruising. And the crazy thing is actually we put on Voyager 1, we put a record, like from a record player, like an old time record player, because that's what they had in the 70s when they built it, that has all kinds of Earth sounds and Earth music on it for presumably aliens maybe to find if aliens ever find this thing drifting out in space. Um, it's never really expected to make it to another star or anything like that. It's, I mean, unless it drifts out there for over 100,000 years or something. Uh, Pretty crazy. So let's keep zooming out. And this is kind of a sort of general dust cloud that's sort of around our sun. And finally, now we have reached other stars. And there's Alpha Centauri. That system is supposedly the closest one to Earth. And again, that one would take about 100,000 years to get to in a normal spacecraft. All right, we're going to keep zooming out even more. And now we are getting to what we would call a galaxy. And galaxies are massive. This is what we would call the Milky Way galaxy. How do we know this is what it looks like? I mean, truthfully, we really don't know. You can see part of this, that sort of milky looking night sky if you're out in the camp area. If you're camping and there's no light out and everything, and you see it actually does look kind of milky, so you can tell that we're in sort of a galaxy of sorts. That's why we call it the Milky Way. The real reason we know we're in a galaxy is that we can actually look out beyond our galaxy, and when we do that, we see other galaxies, and we see other spiral galaxies. And our galaxy, we think, has billions of stars. And when we look out beyond our galaxy, we see there's actually billions of other galaxies. That's pretty insane. The universe, the known universe, so there's stuff that is so far away that light can only travel so fast. So in the age of the universe, it actually hasn't even gotten to us yet. So the far side of the universe, the light that's being emitted on it hasn't even had enough time to get to us yet. So this is kind of the universe that we can see. We really don't know how big the known universe is, but it's massive. All right, so when we're talking about Earth and we're thinking about space, Earth seems really, really big to us, but in reality, it's pretty tiny in the bigger scheme of things. And this is a pretty famous photo. This was the last picture of Earth that Voyager took. This was our spacecraft that we sent out past Pluto. And as it was cruising away from Earth, this was the last photo it could take where it could actually still see Earth. And it's this tiny little blue dot. And, that is a very unique perspective to environmental science. We have to think about Earth as in the greater scheme of things. And we have to think about Earth also in terms of time. So, maybe as you're looking at all that stuff, as we were doing the cosmic zoom out, you might have been asking yourself, where in the heck did all this stuff come from? Maybe you knew about this stuff, maybe not. But there is an explanation of this stuff in science. I mean, using our telescopes and our spacecraft, we can see all this stuff around us, but how it got there is a pretty tough question to tackle by science. And the Big Bang Theory is the scientific theory that sort of tries to describe how this stuff got here. And even it really can't answer the how or why question, but it can answer, we do think that at some point, basically the universe, all the stars and planets and everything else once originated pretty close to the same spot. And I'll go through some of the evidence of that. So as we're looking at all this stuff around us, all these galaxies and stars, what we notice is that actually things are drifting further and further apart. So that is evidence, we can actually track it in real time, that the universe is expanding. The galaxies are drifting in a pattern that is spreading apart. And you can kind of backtrack this pattern. Let's say hypothetically you have a galaxy here moving this way, one here moving this way, one here moving this way, one here moving this way. The idea is that you can kind of backtrack their general direction and see, oh, yeah, all these things seem to have come from a single place, a single point. And that is, I would say, the most kind of easy to understand evidence of the Big Bang Theory. So the idea is that all this stuff got blasted out of one single point in space. How on earth did that happen? That's a little bit beyond science, because we can't do an experiment showing that or how that could happen, because it's way beyond humans. So so we're pretty sure that everything is expanding and that everything kind of came from the same spot. So that's why we call it the Big Bang Theory, like there's some kind of massive explosion that blasted all this stuff across the universe. And the neat thing about the Big Bang Theory is that you can kind of track the general speed of these motions of stars, and we can kind of guess or come up with a time at which all these stars would have been together at the same place. And that time is about 13.7 billion years old. That's with a B. Remember, B, that's a really big number. So 13.7 billion years old, the universe is. Okay, well, that kind of begs the question of, well, how old is Earth, and how did such a nice planet with our wonderful water and air and trees and all that stuff, how did that form out of some massive cosmic explosion? And the answer is that it didn't form right away. So if the Big Bang Theory, the Big Bang happened around 14 billion years ago, and this is our timeline, and if I've drawn this timeline to scale so that every billion years is the same distance, Earth forms about 4.5 billion years ago. And you kind of notice that when Earth first formed, it really didn't look like it does today. It kind of looks like a giant fireball. It looks more like the sun than the Earth, really. And actually, it took about 4.5 billion years for us to get to what we would recognize as today's Earth, where the continents are where they are. And next lecture, I'm going to talk about how this most recent 4.5 billion years. Um, so another really, really interesting and unique perspective that we can look at Earth with in environmental science is time. That Earth is actually really, really old, but the universe is much older than the Earth, and actually, the vast majority of the universe history, there was no Earth. And actually, for a vast majority, we'll learn later in the next lecture, a vast majority of Earth's history, there wasn't much going on either. It took a while before it started resembling an Earth that we have today. And the last kind of mind-blowing perspective that I want to give you is that humans have only been around for about 200,000 years. And we'll talk about how we know that in the next lecture as well. But if I wanted to draw a range for humanity, where I make a like kind of like how this would be, 1 billion years. So I could make like a line that's 1 billion years here. 1 billion. If I wanted to represent 200,000 years on this graph, on this timeline, which is how long humans have been here, it would only be at the very tip. So that width of that line would be how long humans have been around. And actually, that's not even accurate. That line on your computer is probably 2 or 3 pixels wide. It would need to actually be probably like 1,000 times smaller than that. So all of human history from the cavemen to now would fit inside this little tiny red line, and actually that's too big. So that brings us actually to one last little bit of space science, which is how did Earth actually form if the Big Bang happened 14 billion years ago and 4.5 billion years ago, Earth formed, and there was like no Earth for like almost 10 billion years. Well, where did this cool planet that we live on actually form? How did that form? And do we know anything about space that could help us understand where Earth came from? And the answer to that is a supernova. So where do solar systems come from in general? Obviously, most of the other stars that you see in the night sky also have planets that go around them, and solar systems form as a result of a supernova. And supernovas are when a large star basically runs out of fuel and explodes. And basically, the fuel of a star is this nuclear reaction that's keeping it going, and it's also keeping it the size it is. And when it runs out of fuel, it begins collapsing on itself because it's really, really heavy. And in the process of collapsing on itself, it actually gets really, 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 really unimaginably hot to the point where it triggers all these new nuclear reactions. And we'll cover what a nuclear reaction is later in this course. It's a big boom, basically, and unbelievably big boom that happens. And these result in what we call a planetary nebula. And we know these exist because we can see them happen. We can see supernovas happen in the universe around us, in our own galaxy, and in others around us. And what happens is this is the leftovers of this explosion of a star. And you really can't wrap your mind around how big these explosions are. In our little rocket, if we started on this side and wanted to go all the way across this big, massive explosion in space, well, our rocket wouldn't hold up very well, but if it somehow did, we're talking, taking not just 100,000 years, we'd be talking about millions of years to get across this thing. So it's just an unimaginably big explosion in space. And basically, as all this debris and gas gets launched out everywhere, what happens is little pockets of it are a little bit denser with materials than others, and There is last year you learned in physics that there's something called gravity that tends to kind of pull everything together. And so what happens is that in this little near area, everything kind of pulls together, all these gases, and eventually, as they compact more and more, they form new stars and new planets around them. And I'll show you a little video of what that looks like.
But its violent history began well before that, when huge ancient stars that had reached the ends of their lives exploded. These supernovas cooked up all the chemical elements we know today, including iron, carbon, gold, and even radioactive elements like uranium. Over time, gravity took hold, and this cloud of stardust collapsed into an enormous rotating disk, the solar nebula. In the center of this disk, temperature and pressure rose, and a star, our sun, was born. Eventually, gases like hydrogen and helium would be swept to the far reaches of the disk. But closer to the sun were dust grains made of the heavier elements.
They're circling around the early sun and little racetracks, and occasionally grains traveling nearby will collide. Something like this happens in your house. If you look under your bed, you find that little bits of dust are collecting together into big, large dust balls. And something like that must be what happened in the solar system too. If they collide slowly, it can add up to a larger object and gradually grow.
With enough collisions, dust grew into pebbles, and pebbles grew into rocks. And as the rocks grew larger, so did the collisions.
If they collide head-on or at higher velocities, then they'll actually break apart, like shooting a gun at a wall.
But other times, the rocks stuck together. And the larger they got, the stronger their gravity became.
Because of the gravitational attraction between these bodies, you coalesce. Instead of just making a mess, and you do make a mess as well, you build bigger things because gravity holds things together.
In time, gravity shaped them into small, round planets, or planetesimals, just a few miles across.
Gradually they grow from golf ball size to rugby ball size, and then house size and township size. And then one or two of these objects would get large faster than anything else and would become the big boys on the block.
Eventually, some of these planetesimals grew as big as our moon. And then, they combined to form the 4 small rocky planets closest to the sun: Mercury, Venus, Mars, and Earth.
And so that is how Earth got there. And again, we're just a tiny little rock floating around in space in this massive universe. And, that is a very good perspective to have for your life, I think. I mean, knowing that, I don't know, for some reason I'm comforted more than somehow scared by all that. I just think it's neat and cool that all that's out there. And that's how it all works. Well, all right, that concludes our discussion of space. I hope you learned something. I hope that was interesting to you. Unfortunately, if you really like space and space science, that's going to be about it for the whole year. But at least I started somewhere interesting for you. Next class, we'll be talking more about Earth and the last 4.5 billion years of Earth's history and what's been going on Earth for all that time and how Earth has changed, going from a fireball to this lovely planet that we know today. All right, see you next time.